Hello students, in our last episode we worked out many problems involving summation of AP. Today we will discuss some typical problems which are not direct to solve it. Let us take one problem. The sum of n terms of two arithmetic progressions are in the ratio of 3n plus 2 is to 7n plus 15. Find the ratio of 12th terms. Here again, neither A is known nor D is known. Moreover, there are two series involved. It means we have four unknowns. Suppose the first term of the first series is A and common difference is D. And for the second series, it is A dash and D dash. Then what is given to us? We are given that Sn upon S dash n is equal to 3n plus 8 upon 7n plus 15. That means 2a plus n minus 1d upon 2a dash plus n minus 1d dash is 3n plus 8 upon 7n plus 15, which implies a plus n minus 1 by 2d upon a dash plus n minus 1 upon 2d is equal to 3n plus 8 plus 7n plus 15. Again we can write as a plus n plus 1 by 2 minus 1 d upon a dash plus n plus 1 by 2 minus 1 d dash is equal to 3n plus 8 upon 7n plus 15. Clearly, the left hand side is Tn plus 1 by 2 upon T dash n plus 1 by 2. That is n plus 1 by 2th term of the first series upon n plus 1 2th term of the second series. This is equal to 3n plus 8 upon 7n plus 15. Now we require the ratio T12 upon T dash 12. We have the formula for Tn plus 1 by 2 upon T dash n plus 1 by 2 equal to 3n plus 8 upon 7n plus 15. To get this result, we have to set n plus 1 by 2 is 12, which means we must make n is 23. When we put n equal to 23, we get T12 upon T dash 12 is equal to 3n plus 8 upon 7n plus 15, but n here is 23, so you get this plus 8 upon 7 times 23 plus 15, which equals 69 plus 8 upon 161 plus 15, that is 77 upon 176, which is equal to 7 upon 16. Now this is the required answer. So for the given series, the ratio of 12th term of two series will be 7:16. In our previous problem, you might have noticed that we didn't find A and D at all. Similarly, Our next problem also involves similar thing. Here again we have an AP whose PA term is given to be 1 upon Q and Q term is given to be 1 upon P. We have to prove that the sum of the first PQ terms is half PQ plus 1. Now we again assume A to be the first term and D as common difference. So as per the question, we have the following results. Tp is equal to A plus P minus 1 times D, first equation. Then Tq is equal to A plus Q minus 1 D, second equation. But Tp is given to be 1 upon Q and Tq is given to be 1 upon P. Thus we have A plus P minus 1 D is 1 upon Q, A plus Q minus 1 D is 1 upon P. This gives, by subtraction, P minus Q D is equal to 1 upon Q minus 1 upon P. This gives P minus Q is equal to P minus Q upon PQ times D. Now since P and Q are not equal, we can cancel P and Q to get D is equal to PQ. Now we have found D in terms of P and Q. From the first equation we have A plus P minus 1 D is equal to 1 upon Q. But now we know the value of D, so we get A plus P minus 1 upon PQ is 1 upon Q, which gives A is equal to 1 upon Q minus P minus 1 upon PQ. This gives just 1 upon PQ. So we have P minus Q is equal to P minus Q upon PQ times D. But since P is not Q, we can safely cancel P minus Q and hence we get D is equal to 1 upon PQ. Now to find A, we go to the first equation, namely A plus P minus 1 D is equal to 1 upon Q. This gives A plus P minus 1 upon PQ is 1 upon Q. This gives A is equal to 1 upon Q minus P minus 1 upon PQ, that is equal to 1 upon PQ. Thus we find that both A and D are having the same value 1 upon PQ. Having known both A and D, we can find the sum of PQ terms. Now we have SPQ is equal to PQ by 2 times 2A plus PQ minus 1 times D. Now A is 1 upon PQ, so we get 2 upon PQ here, plus PQ minus 1 upon PQ, that equal to 1 by 2, 2 plus PQ minus 1, that is 1 by 2 PQ plus 1, hence proved. Now you may note that in this problem both A and D were given in a non-numerical form, even though we could do it. So remember that in any problem we must look for A and D. Now this implies P minus Q times D equal to P minus Q upon PQ. But already we know that P is not Q, so we can safely cancel P minus Q. So we get D is equal to 1 upon PQ. This implies P minus QD is P minus Q upon PQ, and this gives you D is equal to 1 upon PQ. Now we have to find the value of A. For this, we take the equation A plus P minus 1D is 1 upon Q, which means A plus P minus 1 upon PQ is equal to 1 upon Q, which gives A is equal to 1 upon Q minus P minus 1 upon PQ. Thus, A equal to 1 upon PQ. Actually, when we find the AM of two numbers, we are just inserting one element between A and B, so that A, that element, and B makes an AP. Now, this thing can be generalized. Instead of one element insertion, we can make more insertions, as in the following problem. We have a problem: insert 9 terms between 7 and 37 such that the resulting sequence is in AP. Now look, here we had two terms 7 and 37. In between, we are inserting 9 items. So ultimately, we are having 11 terms. Suppose the remaining terms are A1, A2 up to A9. So we have 7, A1, A2, and so on up to A9, and then we have 37. So in all, we have 11 terms. Our purpose is to find the value of A1, A2 precisely. Now here, clearly, first term is 7, that is A is 7. The 11th term is 37, that is L. We don't know the value of D, so we can find A plus 10D is equal to 37. This gives D is equal to 37 minus 7 upon 10, that is 3. Now we have value of A as 7, D as 3. So what is A1? A1 is simply term 2, that is A plus D, that is 7 plus 3, that is 10. Then A2 is just A1 plus 3, that is 13. In this manner, we can write the terms A1, A2 up to A9 as 10, 13, 16, and so on up to 34. So this problem can be generalized also. We have two terms A and B, and we have to insert n terms so that the entire sequence becomes AP. Suppose they are A1, A2 up to AN. Now, as a result, the sequence of n plus 2 terms A, A1, A2, and so on up to AN, and then B makes n plus 2 terms, and this must be in AP. Once again, we have to find D. A1 is A plus D, A2 is A plus 2D. In general, AR will be A plus RD, where R varies from 1, 2 up to N. Now, in this sequence, B is the n plus 2th term. So, B is equal to A plus n plus 2 minus 1 times D, that is A plus n plus 1 times D, and hence D becomes B minus A upon n plus 1. Now this is a good result to attack such problems. D is always last minus first upon number of insertions plus 1. With this we have A1 is equal to A plus B minus A upon n plus 1. A2 is A plus B minus A upon n plus 1 times 2. In general, AR is A plus B minus A upon n plus 1 times R. Thus, we have found a general method to insert any number of terms between two numbers so that the entire sequence becomes an AP. Today, we have discussed some more typical problems in AP and also found a general method to insert any number of terms between A and B so that the resulting sequence becomes an AP. In our next episode, we shall be tackling a different type of series known as geometry.